speaker and a lot. Happy Monday, everyone. Hope you had a good weekend. And I have just a few housekeeping announcements before we dive in. First of all, for all the students who are enrolled in the class, please make sure to submit 2 reflection papers, about 250 words or more each, in order to receive credit for the class. And the link, if you're wondering, is on the Canvas homepage. I highly recommend you don't wait to the end of the quarter, but try to do those as we go along for the next few weeks. Second thing is that next week on Monday, that's Martin Luther King Jr. Day, so it's a holiday and we won't have a class. And instead, we'll have a special session. It's on Friday, January 21st. That's from 3 to 4 p.m. And I've heard from a few of you that that time conflicts with other classes you have, and that's fine. You don't have to come. However, I think it's going to be a great, fascinating session with Edwin Aoki. And he is a tech fellow and a CTO at PayPal, who will talk about the latest technologies related to blockchain, cryptocurrencies, and how computational math is at the core of these emerging areas. We'll let you know soon whether that class is going to be in person or via Zoom. So we'll send out an announcement really soon. And then finally, during the presentation today, feel free to put your questions in the chat. That seemed to work well last week. And so, Caroline, if you'd like to stop partially through the presentation, we can answer some of the questions or leave all of them at the end. We'll leave about 10 minutes at the end of class for questions and answer period. And I can read off those questions that come through during the chat. So now it's my great pleasure to welcome Caroline McKee back to Stanford, at least virtually today. And I'm really looking forward to your work, Caroline, with Orbital Insights. Caroline has an undergraduate degree, a BS in biochemistry from UCLA. And then she has a master's from our institute, Stanford ICME, fairly recently. So she graduated during that crazy COVID year of 2020. And we always enjoy having alumni back. So a warm welcome there. I sent along Caroline's bio, and I hope that you all had a chance to look at it. One thing that leapt out at me is that she has recently become a Kaggler during this COVID period. And Kaggle, for those of you who are not familiar with that, it's a part of Google, and it's a platform for predictive analytics challenges for datathons. And Caroline mentioned to me that she's formed a team for competition, the Women in Data Science Datathon, which we just kicked off. And by the way, all of you are welcome to compete there. It's open to beginners as well as experienced Kagglers. The topic is energy consumption in buildings and in climate change. And there's a lot of great resources for everyone. So I'll put the link in the chat if anyone is interested. And Caroline, I wish you luck on that. I hope you get to the top of the leaderboard. So, okay.
I hope so too.
So without further ado, I'll turn it over to you, and we're delighted to have you here today. Thanks.
Thanks so much, Karen. Really excited to be here. Hi, everyone. As Karen said, my name is Caroline. I am a computer vision scientist. I work for a company called Orbital Insight, which is actually based probably a few blocks off campus. They used to be based in Mountain View, but a couple of years ago, they made the switch to Palo Alto. And right now, not too many people are in the office, but hopefully we'll be getting back in soon. But yeah, as I mentioned, I'm a computer vision scientist. So what my group here does is we mostly deal with trying to build new models and algorithms and just general approaches to dealing with geospatial data. Let's see if I can, oh yeah, here we go. So yeah, just a quick overview about, we call it Orbital. Basically what Orbital Insight's goal is we want to help organizations understand what's happening on and to the Earth. and turn risk into new opportunities. So, oftentimes when people hear geospatial, people assume that's exclusively just EO satellite imagery, so visual satellite imagery, which a lot of what we do is with that, but we use a lot of different kinds of data, which I'll talk about in a second. But really what we're trying to do is leverage AI to just answer questions about various things happening on the Earth. And this could be kind of, more straightforward computer vision applications, such as monitoring land use change or detecting vehicles, or counting vehicles in a parking lot or something like that. But we've also started to go into analyzing supply chain, and this is actually super cool. I won't talk about this because it's not necessarily what I do, but we've started to create a lot of different supply chain analysis tools by way of anonymized cell phone pings, which is pretty cool. And yeah, if you could ever get someone from that group to come and talk about it, it's super interesting. But yeah, we can also answer questions about global commodities, geopolitical events, demographics, and so much more. I think we all really believe there's so much data out there, and it's so rich, around the Earth. So it's a lot of really cool questions we can answer. And with geospatial data, it often does require some unique methods for analyzing that. It presents unique challenges, and that's going to be a bit of what I talk about today. I'm going to be going through kind of 4 different what I'll call case studies, and they're just representative of the types of problems we work on at Orbital, specifically my team, which is the computer vision team. Some are direct applications that my team has actually worked on, and some are more sort of domain-wide trends, just to give you an idea of the ways you can tailor modeling methodologies and architectures to geospatial data. So just wanted to start out with, just so we're all on the same page, what is geospatial data? And at a kind of foundational level, geospatial data is just information that describes objects, events, or any other feature really with a location on or near the surface of the Earth. So really it's that combination of location information, which usually will take the form of coordinates, so lat long pretty much, and then attribute information, which is the characteristics of maybe an object, event, or what the land is, that kind of thing, where this plane is. And then also you have temporal information. So what's really cool is you can have information about the same place at different points in time, just by nature of how satellites work, or tracking number of cell phone pings over time, that kind of thing. So some examples, I'm sure you can think of many, but obviously I've talked about satellite imagery a little bit, but that can be active or passive. So I actually have that backwards. Active would be SAR, or synthetic aperture radar. So that's something where you have the sensor that actually emits energy and is measuring how much energy comes back. That would be an example where your sensor is directly influencing the environment and then measuring the environment's response. And then some would be passive, which would be these visible sensors. So just as if you had a camera in the air, right? Another would be, and I've talked about this a little bit, mobile location. So those anonymized cell phone pings, you can measure a lot of interesting stuff with that, like foot traffic, or as I mentioned, the supply chain, monitoring supply chain, that kind of thing. Additionally, more and more common is connected cars data, and that's something we're really looking to get into in the next few years, and just a ton of other IoT data, AIS data from ships, GPS type data from planes, all kind of stuff that you can analyze. And again, so much data, a lot of problems that can be answered, and it's really fun to work with. So this talk, as I mentioned, is for the most part going to be about what are some of the unique considerations in geospatial computer vision specifically, because that's the group that I'm in. And yeah, it's going to be by way of case studies, so kind of dive right in. But before we go into the case study, I should talk about the data itself, because I think that is sort of a unique problem that you can have, is the data itself is not necessarily equivalent to a lot of image data you see in traditional applications. There are a bunch of reasons for that, but one would be that geospatial data can have many more channels than traditional image data. So Landsat imagery, for example, which is kind of the standard, I guess you could call it, standard satellite imagery provided by NASA. It can have many more channels than traditional imagery. So, traditional imagery is pretty much RGB, right? But with geospatial data, you have RGB, kind of NIR, which is near infrared, various infrared bands, and bands from all over the electromagnetic spectrum. So that can be difficult if you're thinking of trying to apply any sort of pre-trained model or transfer learning, right? Is that you have many more additional bands to work with, and most pre-trained models don't. They're just trained on RGB. So think about that. Additionally, data is frequently stored as 16 bits or higher, rather than your typical 8-bit. This doesn't, I wouldn't say, present too much of a challenge, but it is something you definitely have to remember, as a lot of pre-trained models or repos are meant to take in an 8-bit image rather than a 16-bit. Usually you can deal with this by simple normalization, which you should be doing with any model anyway, but it's just something to remember. Additionally, data is frequently incomplete or missing, and that's just kind of the nature of satellite imagery. In the way that it crosses over the Earth, you'll often get kind of missing strips, or sometimes something's in the way. So, there are ways we can tackle that. One would be compositing images, which would be, because you do have that temporal aspect of an area being covered multiple times in time, sometimes you can do what we call compositing those images, which is combining them all into one image by maybe, you could do max compositing, which is taking the maximum value of that pixel, that kind of thing. And then you can sometimes get a cleaner image out. But if you were to just take the direct output of the satellite and use that without adequate pre-processing, you're probably going to have some missing data. Also, atmospheric interference. So clouds are a real problem for us. Pesky clouds often get in the way and will obstruct your view. So there are ways you can deal with that, usually just cloud masking. There is actually a lot of research into how you can kind of artificially remove those clouds. But again, the simplest way is probably to just not use that data. But you can see there's a lot of pre-processing involved to actually get good data to use. And then lastly would be, and I think this is, in my opinion, the most difficult, which is dealing with the coordinate system. So by that, I mean kind of georegistration and orthorectification. And what that really means is anytime you're doing any sort of analysis on the imagery, rather than just knowing where you are on the image, you have to be keeping track of where you are on the globe. And that means you're almost exclusively working in coordinates. And it also means that when you're working with multiple images from either the same sensor or different, you have to make sure those are properly aligned, especially if you're doing temporal analysis. And oftentimes that is a lot more difficult than you would expect. And it often involves kind of projecting the images or transforming them such they align to the coordinate system properly. You'll often have points on the ground that are sort of, this is the ground truth, 40 degrees north, X degrees west. And so you have to morph your image so that all of those points align properly. So geospatial data is no joke. So there are a lot of considerations just in the data itself before you even begin modeling. And I would say that's sort of one of the larger challenges, but just wanted to give kind of background there, but I'm going to go into some specific modeling type challenges and solutions, because I think that's a little bit more interesting. So case study number one, which we'll call the simplest case study, but a common problem that you have in satellite imagery is that, say you want to build an object detection model, fairly standard, takes in an image, runs whatever model you want to run, right? Maybe it's RCNN based, or I don't know, efficient dead, or whatever. The issue is that these satellite images can be massive. So it is not uncommon to have an image where the raw image is tens of thousands of pixels by another tens of thousands of pixels. This imagery is huge. And also, it's not uncommon for the objects of interest to be super, super small. So you might have objects which are only 20 by 20 pixels or something. And when you think of, an object being 20 by 20 pixels in an image of 20,000 by 20,000 pixels, that is absolutely tiny. So that's difficult, especially when you consider that in traditional deep learning models, the input image is often rescaled to a smaller size at the very beginning, which when you're working with images of these size will result in a tremendous amount of information loss. And depending on how much you're resizing, you can actually lose those objects altogether. They're just too small for that information to be preserved. And then beyond that, if you're trying to work from a pre-trained model, so even if you're working on a something pre-trained on the COCO data set, which is kind of the class, it's the object detection equivalent of ImageNet. Those are usually pre-trained on medium to large scale objects. They are not pre-trained to see these tiny, tiny objects. So how can we tackle this? Actually, a pretty simple solution, right? What you want to do is what's called slicing aided hyperinference. So in training, you're training on randomized crops from the original image. So you're not resizing, instead you're taking crops, and you're not going to lose that information or potentially lose those objects altogether. And that's pretty simple. But what do you do when you want to run inference on a giant image? Well, you essentially do the same thing. So you're running inference on slices of the image via this sliding window, and specifically a sliding window with some overlap, and then merging the detections. And this may seem simple, but it's actually tremendously important when you're talking about running inference on a huge number of images. And there are a few things that, when you're running this inference, you have to remember. One would be the simple idea of non-max suppression. So I imagine a lot of you are fairly familiar with this, but when you're running an object detection model, if you are using a model that's anchor box based, you're usually going to end up with a lot of boxes for the same image, just by nature of how the grid system and the anchor boxes work for that model. And usually what you would do is run an algorithm called non-max suppression, which essentially will take the box of all these boxes, which overlap to a certain extent. It'll take the box with the highest confidence at a very low level, or a very high level. But that's not going to work necessarily in this situation because of your sliding window here. So I tried to draw this. We'll see. Yeah, not the clearest drawing ever, but say you have these sliding patches here, right? This is your window. This is sliding window 1, and then it slides over and it's here, and then you run it here and here. You can see that if you have an object that overlaps all 4 sliding windows here, where you're going to end up with is a detection here from this sliding window, a detection here from that one, detection here from this one, and here from this one. So you can't just run naive non-max suppression here, right? Because then you're not going to capture the whole object. So what you do instead is what we call union merge. And it's basically of the boxes that overlap to a certain extent, you're going to take the union of them instead of suppressing all but one. And that helps you get a box around your whole object here. And then your confidence will just be equivalent to the confidence of the box which had the highest confidence. And this works super well. So just to show you the types of improvements we see is, I realize this is kind of zoomed out, but I thought it was fairly useful in demonstrating. This is this is just naive inference, so you're not slicing in any way. And then on the right, this is when you're slicing. So you can see, I believe this model is detecting docks and also some cars. So you can see it's essentially missing everything except this slightly larger dock, but not much else. And then when you start running the slicing aided hyperinference, you can see you start to pick up all of these docks here. And that's just because, which seems fairly obvious, but they take up more of the image that you're running inference on. So that I would say is a really important aspect of what we do when it comes to actually running inference. All right, moving on to case study 2, which is perhaps a little bit more in depth. But yeah, here we have task-driven domain transfer. So some of you might be familiar with domain transfer, but essentially the problem that we're trying to address here is, say that we have an existing object detection model and it was trained just using standard supervised learning on a large set of annotated images from a certain provider. So we'll call this provider A provides images in domain A. These images may look fairly different from images of the same area from a different provider. And this is kind of a unique problem in geospatial vision, is that images taken from different satellites or different providers, even of the same area, can look extremely different. So one example would be, you can take images of an area with a kind of, I don't know what they call them, aerial balloons, I guess would be the name, but it's essentially a balloon that sits pretty high up in the atmosphere and can take aerial imagery. But what you often see there, and I'll show you this in a moment, is there's a lot of atmospheric interference, just because you're kind of taking a picture through so much of the atmosphere before you actually see the ground. Things start to look blurry, you lose a little bit of color, and it can be kind of hard to run object detection there. But you can also have a provider that uses a drone, for example, and takes images much closer to the ground. And then those tend to have much more clarity and resolution than those from provider A. And it's not because there's a higher resolution. The GSDs, which is the ground square distance, they're actually the same, which is just basically what distance on the ground does a pixel in the image correspond to. So in both cases, your pixel may be 5 meters. So it's the same, but I'll show you, probably better when I show you, but the images look quite different. So the question is, without creating a new labeling campaign, that's to say, without extracting a ton of images from domain B and labeling them, is it possible to train a new model for domain B when we only have a set of labeled images from domain A? And beyond that, maybe we can even improve the effectiveness of the existing model for domain A by first transferring to a higher resolution domain, or a higher clarity domain. I guess the resolution wasn't quite the right word there. But I think this makes more sense when you see. So this is a domain A image, and you can see generally not as much color clarity, a little bit blurrier, and harder to make out specific objects on the ground. So in this particular case, say we're interested in detecting cars. You can see it's a little bit difficult to make them out. This is domain B. This is, say, imagery that was taken from a drone much lower in the atmosphere. You can see way easier to make out these cars. So say we have a set of labeled images from domain A, can we build a model that works well on domain B? And I'll start out by saying that naively training a model on domain A and testing on B doesn't work so well. The model does not do well. So we need to do something to these images or do something to the model to make this work. So what can we do? Well, I'm sure a lot of you are fairly familiar with what we call Cyclegan. But this is just a generative network, and the classic example is turning horses into zebras and back, or turning oranges into apples and back within an image. But the idea here is you have two domains, sample of images in domain A, sample of images in domain B. How can we make the images in A look like they're from B? So in this case, you have a ton of images of zebras and a ton of images of horses. And how can we turn those into each other, right? For lack of better words. Important to note that you don't have corresponding images. So we don't have an image that is of a zebra and then the exact same images where it's replaced with horse. That's why we call it unpaired. So we just have independent sets of each. So this is what we use Cyclegan for. Just to go over it really quickly, the idea here is you have your image, say domain A is zebra. You have a generator, which is just generally an encoder decoder framework type model that will take in the image, condense the information, and then output the equivalent image in domain B. And then you have a second one that is that takes an image in domain B and then sends it back to A, right? And so the idea here is with Cyclegan, you should be able to take an image in A, send that image into B, and then send it back to A. And so this is trained with a fairly framework that's consistent with how GANs are trained in general, which is the generator discriminator framework. So say you take this image of zebra and you send it to B. What you do then is you have a discriminator network, which tends to just be, I don't know, a standard network, a standard CNN that will take in two images. And the idea is it decides which one is real and which one is fake, right? And at first, that's going to be super easy because the generator is probably really bad. But you're going to then back propagate that loss back into the generator. The generator is going to get a little bit better. Okay, how can I fool the discriminator a little bit better? And the idea is they're really fighting each other. So the better the discriminator gets at fooling the generator, the better the generator has to get at fooling the discriminator. And again, you've probably heard this before, but in setting up that fighting schema, both networks tend to get pretty good. And so that's how you train this generator portion. And obviously you do the same for the other generator. But with Cyclegan, there are a few more losses to consider. And that would be the most important of which is here it's called the L2 loss, but you'll often hear it called the reconstruction loss. But that's telling you, okay, how well is this network doing if I take an image in A, send it to B, and then send it back? Now, hypothetically, if this were a perfect network, that reconstructed image should be the exact same as it was before it got sent in. And if it's not, that's considered a lot. It contributes to the loss. So we just use the L2 loss, which is essentially the Euclidean distance between these images, right? If they were the exact same, that loss would be 0. So that's another loss. And there's one more loss that's actually not depicted here, but we call that the identity loss. And that is just if you were to send this image in domain A through the B to A generator, basically nothing should happen, right? Because it's already in A. And that helps a little bit with color composition. But yeah, this is Cyclegan. And so maybe we can use this to transfer between domain A and domain B here. And just want to talk about a little bit of an improvement that has happened in the past few years. And this is using what we call patch-based contrastive learning. So contrastive learning, I'm sure you've heard of it, but it's become really big in the past few years, especially in the areas of self-supervision and models that take in a tremendous amount of training data, like a lot of Google's models or can't remember what the other one, big one is, but they'll essentially take in all the images from the internet and get this incredible pre-training. But in this case, how can we use this? So the idea behind contrastive learning is always that you are taking in a batch, and within that batch, there's usually one matching pair, so to speak, and all the rest are not matching pairs. And you're teaching that model to find the matching pair and say, okay, these ones are not a match. And so in this case, how can this help us? Well, say we choose random patches on the image. What we want to do then is encourage the patches from the image in both domains to be similar within a learned feature space, so within an encoded feature space relative to the others. So basically we want this horse head to be more similar to this zebra head than to random other parts of the horse image. And this is an improvement that can be seen in a lot of unpaired translation tasks. They seem to be trending more towards using this contrastive learning, and it turns out it actually helps in this case a lot, as well as we're interested in a lot of the smaller objects in the image. This helps with that local information. So incorporating that into the GAN, I don't want to go too deeply into this architecture, but this is called DCL GAN, and that stands for Dual Contrastive Learning GAN. But the thing I want to point out here is we're using this exact idea in terms of retaining mutual information between corresponding patches. And we're doing that exactly here. So when we're translating from, this is cat to dog here, but translating from cat to dog, the idea is the generated fake images red patch here. So this dog's eye should be more similar to the real inputs corresponding patch, which here is yellow, while dissimilar to the blue patches. And again, this helps a lot with the local type of information. So we now have a way to translate an image from one domain into another, which is super cool. But there is a small problem, and this is a common theme, I would say, in GAN images that are generated by GANs. And that's that GANs are generally used to create realistic looking images to the human eye, or images that adhere to the general distribution of a set of data visually, right? So the problem you can run into is that a fake generated image may look natural to the human eye, but that doesn't necessarily mean that's going to be suitable for downstream tasks. So in this case, we're interested in running object detection in that new domain. So how can we ensure that the new fake drone image, domain B, will actually be useful in training an object detector and not just look right, so to speak? And this is something we introduced, my team came up with, and it's worked pretty well. I'll show you the results in a bit, but we call it detection guided GAN. And all you're really doing then is training the detector together with the GAN. So this is something I think is so cool about deep learning is, it's so easy to translate this to a multitask framework by simply making the loss function include loss from whatever tasks you're interested in. So really, all that's happening here is we're adding on an extra head, so to speak. But the idea is once you've taken an image from domain A and translated it to domain B, remember that you have the labels for that image in domain A. You can then simply run object detection on that image in domain B and update the generator accordingly. So this is actually works really well, and a few other papers have tried this, but the idea is start with your pre-trained object detector that's trained on the domain A, because you don't want to start from scratch, or else you might have some convergence issues. But you're going to use this detection loss, standard detection loss, and add it as an additional term into your overall loss, your generator loss function. And so in addition to generating images that fool the discriminator and adhere to these other losses, you're also forcing this network to generate images that also work well in terms of this object detector, and this detector will be able to detect the objects of interest in. So yeah, that's kind of how it works. You're updating those generator weights, and additionally, you can update the detector weights itself. So both the generator and the object detector are getting better. So again, sort of not fighting this time, but forcing each other to get better. And these are the results we see from qualitative results. This is our real A image. This is what it looks like when we translate to B. You can see generally more clarity, more color composition. It's not perfect. It is really hard to go in this direction, A to B, because again, you're sort of introducing information instead of losing it. But overall, it's looking pretty good, and this does help the detection quite a bit. Again, B to A, much easier, but also very realistic looking results, I would say. In terms of the actual performance, this is pretty cool. So training set domain A, which is those blurry balloon ones. If you train on A and test on A, you can actually build a pretty good model, which we were a little bit surprised about. But you get mean average precision at IOU 50 of 80.3. But this is what I mentioned. If you train on A and just naively test on B, that drops tremendously. That model does not know how to detect objects in domain B. If you run images from domain B and translate them from domain A and translate them to domain B via this GAN without that object detection branch, so just the original DCL GAN, you're back up to 0.65 mean average precision in domain B, which is still pretty cool because you've now built a model that works pretty well in domain B without actually having to create any labels in domain B. And then when you add that object detection branch there, that bumps up even more. And we were hoping it would be even better than the supervised training and testing on domain A, but maybe that was a little too much to hope for. But 0.74 is coming close to the performance of the domain A model. So pretty happy with that. All right, I'm going to keep going. We only have 20 minutes left. Wow. With case study 3, so switching gears a little bit actually. This goes back to contrastive learning still, but how can we do self-supervised pre-training in geospatial deep learning, and what does that look like? So we talked a little bit about contrastive learning, but just to give you an overview of what we're looking at in this context, the goal with contrastive pre-training, you'll often also hear it called self-supervised pre-training. How can we teach the model to learn to recognize the features in this data set, even if it doesn't know which features correspond to which labels, because at this point we don't have any labels, right? So this is a model called SimClear, which kind of started the whole, I would say, transition to contrastive learning based pre-training. But the idea here is you have an image, you're going to augment it in 2 different ways. So that could be color jitter, random crop, rotation, whatever. In the paper, I think they found that color jitter and random crop work the best. But you're going to augment that image in 2 different ways, run it through your CNN. This is sort of the encoder, and this is ultimately what it's going to become your backbone for your downstream tasks. So this is what you're trying to pre-train right here. You get out a representation, and usually you'll stick it through an MLP head. I think maybe 3-layer MLP is what they used, if I remember correctly. But the idea here is you want the ultimate embedding or representation here to be similar for different augmentations that came from the same original image, and very dissimilar from representations that came from different images. So it's essentially getting the model to learn the features that come from this image and learn that they correspond and learn to look for them, even though you're not saying, okay, this is a dog. But then when you do say this is a dog, the model's already going to have a leg up in terms of recognizing the features of the dog because it's already learned them when it's had to pair the matching dogs together. So that's the idea. And this works really well for general tasks, does work well for remote sensing images as well, but there's actually a way we can do better, which is remote sensing and geospatial data specific. And that is to use temporal information to obtain pairs of images rather than exclusively doing artificial augmentation. So that's the crop color jitter. What we can do is obtain pairs of images from the same location at different points in time. So different times during the year. So it's actually called seasonal contrastive learning in the paper. But the idea here is these seasonal changes probably provide more semantically meaningful, that's to say, information that would be more helpful for the kinds of tasks we're trying to do than just these artificial transformations, because you can see how much the land changes over the course of the year. So this would be useful if you're trying to do, we have a lot of land use and land change models, usually semantic segmentation based. So yeah, to go through this really quickly, you have your query image, which is your original image, and it's pretty similar to the SimClear schematic that I talked about above, but the difference is you are augmenting it both synthetically, just like before. So this looks like it's a vertical or horizontal flip, but you're also augmenting it via the temporal augmentation, which is those different seasons. So what this image looks like at different times in the year. And that's this T0 and T1 here. And you're using the same encoder for all different wings, I guess you could call them, all different pathways. These are shared weights. And then you are projecting that just by way of another MLP into 3 different subspaces by 3 different heads. And subspace 0 here is invariant to all transformations, whether synthetic or temporal. So the idea here is the positive pairs or positive group is all of these. The negative group is random other images. Subspace 1 is invariant to seasonal augmentations. So the matching pairs are just the seasonal augmentations, and the synthetic augmentations are not part of the positive, they're part of the negative. And then lastly, Z2, subspace 2 is invariant to the synthetic. So the positive pairs is just the synthetic augmentations. And projecting it into these 3 spaces actually does a lot better than just taking this single space alone, which would be the natural thing to do. But yeah, then it's just like SimClear where you're trying to pick out the matching pairs. It's that same contrastive learning idea. And this encoder F can then be used as a backbone for downstream tasks. And it works really well in terms of using that as your pre-trained backbone instead of maybe starting from ImageNet or something. And it does even better than if you were just going to start from that SimClear setup where you're just using synthetic transformations. All right, got a few minutes left here, so work on case study or talk about case study 4 real quick.
And Caroline, just a heads up. So we wanted to leave at least maybe 5 or 8 minutes at the end. So maybe 5 more minutes on this case.
Absolutely. This is the last one.
Great.
So case study 4 is when you have, say, compute limited. You're trying to create as lightweight a model as you can, and say you want to run unsupervised change detection. So the problem, as I've gone through the problem with all of the case studies, the problem here is that, as I've said, remote sensing or geospatial imagery is usually huge. And if you're trying to run analyses over large areas, that takes a tremendous amount of compute power. And this can be super costly, especially when the processing involves deep learning models, which, as you know, usually require the use of GPUs, which are not cheap. They're getting cheaper, but not cheap when you're talking about running it over the whole globe. And beyond that, it can be super costly to obtain the necessary labels to train supervised models. So maybe sometimes you'll want to do something in an unsupervised manner, both because it's cheaper and it might provide you more flexibility. And you'll see what I'm talking about in a minute. But let's say we want to make a change detection model. How can we do this in a lightweight and low cost way? So by change detection model, I mean model that takes in 2 images taken at different points in time of the same area. And we want to know what are the main changes between those images. And usually in practice, this will be something like land use change, like maybe deforestation or the construction of roads, that kind of thing. And we want to know what changes have happened here. So here's an idea of, just to give you an idea of what I'm talking about, we have this area and you can see there's been construction of new roads. I don't know if you can see my mouse or not, but construction of new roads in the lower left, and the road in the upper right has been very much extended, along with some additional construction in that sort of built up area on the right, and also below the main road on the bottom. How can we find the changes, given that there's also some kind of not large scale, but general shifts maybe in the satellite, the output of the satellite, and then some clouds you can see all over, and we don't want to detect those. So a kind of naive idea would be to take the difference image and then threshold it, which you would get, it would probably, this is actually a pretty clean image relative to some of the images we take in. So you'd get some result, but it would not be super clean in that, again, you can see there's clouds and just like small, very light changes in the land structure and that kind of thing. So what we can do is we can actually use a non-deep learning approach instead. And I think this is pretty nifty, but the idea is you'll split that image into, we use 5x5 neighborhoods, 5x5 tiled pixels here, and just run a simple PCA on that vector set to extract the eigenvectors, right? And then, so now we have these eigenvectors for this sample set here. There's not a neighborhood for each pixel, but it's a big enough sample size such that we've been able to extract some pretty good eigenvectors for this diff image. And then we can build an actual feature vector space by, for each pixel, extracting the neighborhood around it, flattening that, and then projecting that onto the first X eigenvectors for that above sample. And what that actually allows us to do then, and this is pretty cool, is we can then run clustering on those feature vectors. And generally speaking, the changed pixels are all going to be part of the same cluster. And we're having a few assumptions here, but generally this model will not work if most of the image is changed. We're looking for just small changes. So what we can do is take the cluster with both the lowest number of assigned pixels and also the highest mean in this diff image, just because changes in the diff image usually have a higher value to be that changed cluster. And this allows us to remove so much of this noise from the diff image and actually get a clean change image right here. So I really like this method. I think it's kind of shows that you don't necessarily need to throw a crazy GAN at every problem. This works extraordinarily well in practice with just simple PCA and extracting some of the eigenvectors and projecting there. So that was the last case study, finished, yeah, about in time. But if this sounds at all interesting to you, come work for us. We're currently looking for more CV scientists. Our team's got a lot of different models on the roadmap for the coming year. I think it'll be a really exciting year. But we also have a data science team that doesn't deal with CV type imagery as much, but does a lot of the geolocation data and that kind of thing. And then also just backend developers and UI developers. So if you're interested, here is the link to apply. But yeah, we're located right next to Stanford, so another perk.
Fantastic. Thanks so much, Caroline, for all of these different case studies. They're amazing. Here, let's see, there's a few questions here. The first one is, for this data, and I believe it was case study 1, do you usually have sufficient data, or do you use data augmentation techniques for the training of deep learning models?
Case study 1. Okay, so that
Might
was
have
the
been case
slicing.
study 2, but in general, I guess.
In general, no, we absolutely do use data augmentation techniques. That's super important, because with remote sensing imagery, you generally have a lot of imagery, but it's all unlabeled, right? You have images of the entire Earth, pretty much. And in some cases, you have imagery of the whole Earth daily. But the issue is, if you're doing a supervised task, you're hurting for labels. So you definitely will use some data augmentation there. But as much as we can, as I talked about in case study 3, we want to do self-supervised pre-training beforehand, because again, we do have all this unlabeled data. So how can we use that before training the model? And then maybe we don't necessarily need quite as much data when actually doing the supervised portion. But yes, absolutely, data augmentation, important.
Great. And then Gianluca's question here, how often do you update the models for a specific application? Do you retrain when new satellite images become available? Is there a concept of backward compatibility so that your models are always improvement of the baseline rather than completely new architecture?
Mm-hmm. Yeah, so I can't really put a number on how often we'll update the models, but we'll update them in 2 ways. So yes, when new imagery becomes available, Planet, you're probably familiar with another geospatial company. They deal with more with providing the imagery, but they recently released a new type of imagery called mosaic imagery, and it's really nice imagery. So when new imagery like that comes available, we do try to train new models. But also what's really important is a feedback loop. So in terms of using our models, users are logging into, it's called the Go platform, but it's a platform and they're running these models, and they can also give feedback, which is essentially saying, no, that's not a airplane, that's a ship. I would hope it wouldn't make that mistake. But what then we can do with that is say, okay, this is an example, right? And the model got it wrong. And if it's getting it wrong, it's probably a hard example. So that would be really useful to add to our training set, and retrain the model there. And of course, we do like to try and update architectures as they advance. I think it's not necessarily realistic to update to the state of the art every time a new state of the art comes out, because they seem to come out every week. But when large scale changes in architectures are coming out, we'll try to incorporate those.
And I had a question actually about how long it takes to run these models. Are we talking about, for instance, you mentioned DCL GAN, or even more sophisticated models there with DG DCL GAN. What's the time scope for running these sorts of models?
Yeah, so everything is done on the cloud infrastructure. So we have obviously a lot of GPUs hooked up, but available. But even then, I think it's very model dependent, and it's dependent on how big an area you're trying to run it on, because usually you do have to tile that area, because again, it's just not realistic to have an image of thousands of square miles sent through that model. So you're usually tiling it. But in my experience, they run, pretty fast. That is a consideration, obviously, both in terms of the cost for the compute and, we don't want a user to be waiting for a long time. So that is part of the reason we do have an interest in models like in case study 4, where maybe they don't use GPU and they can run lightning fast. But you're not waiting for days generally, unless you're trying to run large countries or something.
Mm. Okay, good to know. And here's a little different spin here. Since you came from a non-tech background from undergrad, did you face any issues while searching for internships or full-time jobs?
Yeah, it was a pretty big, so yeah, as you mentioned, my undergrad was in biochemistry, but I had been doing some research my senior year of undergrad. That was actually neuroimaging research that involved a lot of computer vision, so I became very interested in that. So I definitely faced issues making the actual switch in terms of the coursework at Stanford was a lot of work for me, just because I, didn't necessarily have the background that a lot of the students did. But after persevering through that, I would say anyone here as a student is in a really good spot to search for or obtain an internship or full-time job, because the program prepares you extremely well. And people are always really excited to see that you came from ICME. So
excellent to
but
hear.
yes, it can be done.
That's a great stopping point. And of course, Carolyn has her link here. So hopefully you'll find some good ICMers to join you at Orbital Insight in the future.
Yeah.
And thanks everyone for coming today. And again, looking forward to the next class on Friday, the 21st of January, 3 o'clock. So a different time as well as different day.
Thank you,
Right,
Caroline.
thanks, everyone.
Thank you.